Hello, everybody. So this is an extra lecture where I will work out some problems related to Chapter 22 in OpenStax, which is about magnetic fields and magnetic forces. So let's begin. The main idea of the chapter is that moving charges they experience a force when in the presence of a magnetic field. So we could say moving charges feel magnetic fields, and magnetic fields are denoted by a B letter. This is by contrast to electric fields, which are with an E. And then the other concept is that moving charges create their own fields. So we also have that. And there are just a couple of major equations to know for the chapter. The one associated with sort of feeling the fields is the force due to a magnetic field. So that's given by the charge that's moving times its velocity crossed into the B field. And for moving charges, the important equation there's a couple of versions of it, but it's that the B field that's created is equal to there's first a constant, and that's mu zero over 4 pi. And then it's similar to the electric field, but you need a moving charge, so you have QV. And then it's cross into the r hat vector. R hat is the direction in which you're looking. And then it's divided by r squared, which is the distance that you are away from the charge. So if you have some charge Q, and if it's moving at um, some speed V, or your velocity V, and if we're looking at it some distance away, you start at the charge and you're looking, say, here, then this distance right here, that's your little r, your r hat is just this direction, the direction in which you're looking. So there's another version of this that is used, and that's when you have a line of charge. So if you have a line of charge, meaning a current, so you have a current I that's moving, this will also produce a magnetic field, and the magnetic field is that's going to the right here. It's going to be out of the board or notebook here on the top and into the board or notebook on the bottom. And it makes these loops, so it comes out and then goes into the board, and the magnitude of the field is mu zero over 2 pi, and it's proportional to the amount of current, and you just divide by r. So pretty simple expression where r is how far you look away from the current. So if you're looking at some distance r away, like over here, this would be the magnitude of the field that you see there. And of course, the direction is according to the right-hand rule we discussed in class. Now, something that I didn't mention, I guess there's some names for these things. This is generally called Ampere's law. Um, and also, it's kind of interesting, this constant, it actually has an exact value and it has a pi in it. It's 4 pi times 10 to the minus 7. And then there are a bunch of, well, not a bunch, but there are two main ways in which the unit is written. One way is what we had, the newtons per amp squared, but I'm going to write it the way the book does it in one of the later sections. It's Tesla times meter over amp. This is actually the same unit. The units of magnetic field is Tesla, so this is. And you can use this force formula to figure out how these units are connected. So let's just do a quick unit check to see what that's about. So if we do a unit check on this Tesla meter per amp, we have Tesla meter per amp. And let's see, so a Tesla has to be related to a Newton as follows. So if you have from the top formula there, from this force formula, you know that you have Newton is equal to a Coulomb times a meter per second, because that's the velocity, times a Tesla. So actually, you can see that that means a Tesla is the same as a Newton second over Coulomb meter. So I'm just solving for T over here. And if I plug this into this unit, the Tesla meter per amp, then I just get Tesla. Well, I'm replacing the Tesla, so I get Newton seconds per Coulomb meter times a meter over amp. And the meters cancel, and I just get that this is Newton second per Coulomb amp. But a Coulomb per second is just a amp. So this is a Newton per amp squared. So it's the same unit. So this whole thing is also equal to Newton per amp squared. So I think it's worthwhile to check out units sometimes to make sure they work. If you see an unusual unit, it might be one that you're familiar with. You just have to check to see if the units are equivalent, especially in this class where there are so many different kinds of units. But they're all related to each other because the only new true unit is the Coulomb, which is the amount of charge. Okay, so we are going to do 3 examples with these different concepts. And the 3 examples are going to be the 2 parallel wires, which I kind of talked about a little bit already. This was the demo of the lab. So it's going to be our examples. The other thing to talk about is motors. So we'll have to mention motors as an example. And the third thing we need to talk about is the Hall effect. We're actually going to do these in opposite order of the book. In the book, the Hall effect is first. So book is in opposite order. But it's okay. All of these are just examples of the same concepts. The really main things to know are already here. It's that moving charges generate fields, and that moving charges also feel the fields. They experience a force when there's a magnetic field around. And we have to use this cross product to understand which direction these forces and fields are going. And the cross product is accomplished with the right-hand rule. There is a little bit of a trick for problems. If you don't like the right-hand rule and you just want to do things sort of by hand, or, you can actually kind of do the right-hand rule on the 3D coordinate system. So let's say you have a 3D coordinate system. Let's say we put our y-axis like this, our x-axis like that, and this actually means that the z-axis has to come out at us, out of the board. If you have your equations, your coordinate system set up like this, you can actually just list the cross products for all of the different directions. And it goes like this. So if you cross x hat, the direction along positive x, into the direction along positive y, that just gives you z hat. And then it's all what are called cyclic permutations of this relation. You basically just can move each of these letters, like Z, over to the start, and you move the X over to the second position and the Y over to the third position. And you just list all of the cross products. So the next one would be Z hat cross X hat is equal to Y hat. And then finally you have Y hat cross Z hat is equal to X hat. And then if they show up in any other combinations, they'll just be the reverse of these. And when you reverse anything in a cross product, you take it in the opposite order, it just picks up a minus sign. So if you have Y hat cross X hat, that's minus Z hat. And if you have X hat cross Z hat, that's minus Y hat. And if you have Z hat cross Y hat, that's minus X hat. So that might be useful for you if you don't like doing the right hand rule and you prefer to just set up a coordinate system, and then you can just have this table recorded somewhere where you just look up what the cross products are. It's just a little bit of a trick. Since I am on video, I'm going to use the trick, I think, because it's kind of hard to demonstrate right hand rule using this notebook. So I'm going to use these. I'll show you how it works. Okay, so let's begin with the two parallel wires. The idea there was you have one wire, another wire, and you have currents going in opposite directions. So I'm going to have current going this way. I'm going to have it be the same current, I, on top. And I'm going to have the same current just going in the opposite direction on the bottom, I. And I want to calculate the force on the top wire. So, and I'm going to give some numbers now, some actual numbers. So I'm going to say that the separation between the wires, say D, is 1 millimeter. And I'm going to say we're looking at a segment of wire that's 20 centimeters long. And I'm also going to assign a value to the current because I want to actually calculate the value of the force. So it's going to be 5 amps. Okay, so our question for this example, again, this is example 1. Our question is, what's the force on the top wire? Okay, so what should we do first? The first thing to do is to establish what the B field is. So remember, the bottom wire is going to create a magnetic field. And we already saw how that works with the right-hand rule. This wire now has a current moving to the left. If it's moving to the left, then up top, it's making a field that's actually into the board. So up here, there's going to be a B field that's into the board from the bottom wire. And that's going to be our B. So the first thing to do is calculate this magnitude of B at the location of the top wire. We already saw the formula for that. That's up here. All right, it's this Ampere's law. So we'll just write it down. It's mu 0 times I over 2 pi. And then the distance we care about, we're looking for the field at the location of the top wire. So this is D, the separation between the wires. Okay, so now the tricky part is the force. So we know what is our formula for force. Generally, it's this thing up here, the QV cross B. So let's we have to play around with this a little bit to figure out what actually happens here. So let's figure out, first of all, since the B field is going into the board, let's set up a little coordinate system where we're gonna let this be the X direction, this is the Y direction, and so Z is sort of coming out at us like this. In that case, since B is going into the board, then we know, and let me just call this magnitude like B, just like just the letter B without the vector symbol. So if this is our coordinate system with Z is going out of the board, if B is going into the board, that means we can write the B vector as the magnitude times the direction, which is minus Z hat. So if we want, we could just write it as minus B Z hat. Now, what else do we know? We know the charge is moving with the current, and that's going to the right. So that's going along positive X. So it's a little tricky. We need some connection between the current and the charge. And we have some sense of how to do that. If you remember, if you have a wire, what does it look like? It looks like this, right? There's a cylinder, right? It's a big cylinder. It's a metal cylinder. It has some cross-sectional area A. And it's got electrons moving in it in sort of the opposite direction as the current. If there's a current going this way, right, that means the electrons are going the opposite way because they are negatively charged, and current, remember, is always in the direction of positive charge. So there's a bunch of little electrons, and they're all moving that way. And they have a certain drift velocity. The drift velocity of the electron, like you should go back and sort of see how we derived that previously when we were talking about drift velocity and resistance and stuff, but it was related to the current and divided by the charge times the density of electrons times the area of the conducting surface. This was the relationship between the drift velocity and the current. And this guy is the number of electrons per unit volume of the conductor. Okay, so that is what we need. And that is what's experiencing the force, is those moving charges, the moving electrons that are moving with this drift velocity. So that's one thing. And now we need the amount of charge that's actually in there. So the amount of charge, so Q, the amount of charge in the wire that, oh, and we should, okay, before I go there, I should call this 20 centimeters something like L for the distance for the length of the wire. So, okay, so we have our drift velocity, that's one thing. Now we should figure out like how much charge is actually in the wire because we need to know that to know how much charge is experiencing the force. So, how much charge Q is in the wire? Well, that's kind of easy to figure out because if you know the cross-sectional area, this is A, and if you know that the length is this L, this 20 centimeters, then the number of charges in there is going to be, well, I guess we could be very careful and make sure that we put a negative sign because it's, it's the electrons are negatively charged. So we can do that and be very careful. in the end, it won't matter too much as long as um, we end up having that this Q times V is in the right in the right direction, like to the right. But we'll see that it works out. So anyway, the total charge is negative E. That's the charge of an electron. Now you need the density of electrons times the volume, right? Because if you have density, the number of electrons per volume, then you can get the total number of electrons by multiplying by the volume. And the volume is just A times L. This is the volume of the cylinder. Okay, so now we have basically everything we need. This is how much charge we have in the wire, and each of those charges, the electrons are moving with their drift velocity, and they're moving in the negative x direction, right? Because they're moving opposite of the current. So let me, I guess, use blue again. So the velocity of all these electrons is just minus the magnitude, which is the drift velocity times x hat. And again, it's good to remember our coordinate system, this one. All right, so there we go. And now let's put it together. All right, let's put together these two things and figure out what this quantity is. So the force experienced on the top wire is equal to Q, which we figured out is E, density of electrons, area, L. All right, this is our Q. Our V is minus the drift velocity, x hat. That's our V. And this we're going to cross into B, but our B is minus B Z hat. Okay, so there's three minus signs and two of them cancel, so there is an overall minus sign. Now we have to substitute in for the drift velocity, which is just the current divided by E and E times A. So you see there's going to be some cancellations. Then you have an overall factor of B. Again, there's an overall minus sign. And then for the vectors that are left over, you just have x hat cross z hat. And if we look at our table up here, let's see what that is. X hat cross z hat. We have it here. It's minus y hat. So x hat cross z hat is minus y hat. You can actually just tabulate these and just keep them somewhere, like on a little sheet of paper or something. You just look them up. So this is minus y hat. And now the minus signs fully cancel, and these guys cancel, and you get a kind of interesting result. You get that and the areas cancel also, so that's handy. So you get a very simple result. It's the length of the wire times the amount of current times the B field, and it's in the positive y hat direction, right? So what does that mean? It means that this top wire is experiencing a force upwards. This is the way the force is. It's in the positive y direction. So this is the force on the top wire. Okay, so there's one more step. We should plug in for the magnitude of the B field, which was here. We already had that worked out, so we just have to take this guy and plug it all the way into there. And that gives us our sort of final expression. We're going to plug in numbers just to see what we get. All right, so what do we get? We get L times I. We plug in for B and we get mu 0 I over 2 pi D. And it's all in the y hat direction. Now something interesting happens. You can see the force is proportional to I squared. So the more current you put in, like the larger the force is, substantially, right? It grows as the square, and that's because the current is both creating the magnetic field and is that same current that is going in the opposite direction and feeling that magnetic field in the top wire. So, okay, you have L mu zero I squared over 2 pi d. And that's in the y hat direction. So let's plug in numbers. L was 20 centimeters, so that's zero point 0.2 meters. Meters. Mu zero is 4 pi times 10 to the minus 7. And I'm going to put newtons per amp squared because it'll make the unit cancellation really obvious. Because here we have 5 amps for the current, and that's squared. So you see the amps cancel out. And on the bottom, you have 2 pi. And then what did I put? I put 1 millimeter, I believe, for the separation. Yeah, so in meters, that's 0.001. Okay, so there's some nice cancellations, right? These amps cancel and these meters cancel, and you just get an answer in newtons. At this point, I would need a calculator, so let me just do the calculator. Um, Real quick here. So let's see. We could do a little more cancellation, I guess, but I think it's okay. We'll just plug in to the calculator. See, the pi's will cancel actually on the top and bottom, but that's all right. You can just plug all of them in. All right, I get that it's let me just double check here. Yep, I think I got it. I get a 0.001 newtons. Small. It's a small force. So that's why in that demo I showed you from the lab, you don't see very much effect when you crank up the current. It does move the two wires apart, but it's not the world's biggest effect. So that's because the forces are small, which you now see. Okay, so that's example one. Probably one of the more complicated ones because it involves creating a field with one wire and then sensing the field with another wire. And along the way, we've found this nice expression for the force on a wire due to a magnetic field. This is sort of important to remember. So the force on the wire due to a magnetic field, the magnitude of that was the magnetic field times the current times the length of the wire. So that's kind of a cool formula we got along the way. Okay, so next let's talk about motors. A motor is a way of converting electric energy into mechanical motion. So you're going to take electric energy and convert it into basically kinetic energy. And the way that works is by spinning a loop. So what happens is, say, you put basically a loop of current in a magnetic field. So I guess we're using red for current, so let's do that again. Imagine running a loop of current, a square loop, say, around like this. And, there's some battery attached to this. But let's imagine also that it's attached to like uh, a cylinder that can spin. So I didn't draw this the best way, but I think I might have to redraw it a little bit. But the loop is allowed to spin around this direction. And we want to assign some length. So we're going to say that I want to draw it in a kind of symmetric way. So let me try to draw it so that the left and right sides are roughly the same um, width. So, okay, so we're going to have a width of the loop. So this is going to be the width over 2, W over 2. And this is going to be like a length. Okay, so, and then it's the same length over here, L. So we got, it has like a width and a length. It's a square loop. I know I didn't draw the best square, but, and it has some current I running in it. Okay, and then we have to have a magnetic field. So let's put a magnetic field. Um, and it's convenient to draw the magnetic field this way. We're going to make the magnetic field go to the right this time. I know we've been drawing magnetic fields in and out of the board, but this time it's easier for to start with it going to the right. Okay, so what happens? Uh, we know that the only time moving charge can sense the magnetic field is if it's perpendicular or, not parallel to the field. So that means that these top wires, they feel nothing. So the top and bottom, they're not going to feel the magnetic field because they're parallel to it. See, the current is moving with the B field on top and bottom. So top and bottom portions uh, feel no force. Okay. But the left and right will feel a force because the current there is perpendicular to the B field. So let's do the left side first. So this is going to be our left side of the loop, and this is going to be the right side. So on the left, um, there is a force. So let's figure out what the force is. So we know that the force is, QV cross B. Now it's very similar to what we did before, like in the last example. We know that this QV can be converted to a current times the length of the loop. So if we go back and we see what happened there with the QV, um, the QV part ended up just being this stuff right here. There was this amount of charge, and this was the drift velocity. So let me just actually take this part and have it separated out here so we can use it. So for a wire with a current I, and let's going in direction x hat, we have the following: that QV is just well, I guess we can redo the calculation a little bit. It was minus E density of electrons, A times the length of the wire, and we have the drift velocity. And the drift velocity, I'm just going to plug in for that. If I look up here, drift velocity is the current, right? The current divided by all this stuff, which canceled out. And it was along the negative x hat direction. So actually for QV, just this quantity, what it ended up being is quite simply the two negative signs canceled, and we just had the length of the wire times the current and it's in the x hat direction. So that's actually QV. Um, that's important. So whenever you see a QV, we can just replace that with the length of the wire times the current going in it times the direction of the current. So this is just, this x hat is the direction of the current. Okay, so let's specialize to this example. Now we're going to set up our coordinate system. Similar way, we're going to have x, or no, we're going to have y up here. We're going to have x, and then z hat is coming out at us like that. So, all right, so for the left side, what should the force be? This QV is going to be replaced by the length of the wire, which is just L, times the amount of current. And then what's the direction of the current? It's up, so it's in the y hat direction. What about B? This guy, well, it's whatever the magnitude of the magnetic field is, and it looks like we've defined it in the x hat direction. So plugging in for those things, we get that it's Li y hat crossed into B times x hat. The B part is a constant, so we just pull out a common factor of LIB, and it's y hat cross x hat. Now this thing right here, we can go look up what it is. It's going to be, let's see, we want y hat cross x hat. It's minus z hat. So this is minus z hat. So in the end, the force on the left side of the loop is equal to minus LIB z hat. And z is going out of the board at us. So it's negative z, so it must be going into the board. So this wire on the left experiences a force that's into the board. So there's a force that pushes this wire um, into the board. So actually, I guess I drew the rotation differently. It's not coming out at us. The rotation is actually the other way. This loop in this magnetic field is going to rotate this way into the board. And we can check that that's consistent with what happens on the right. So let's look at the right side. Okay, it's very similar calculation on the right side. What do we have? We have it's still the same length of same length of wire L, same amount of current I, but now it's going in the negative y direction, so we better put a minus y hat. And then that gets crossed with bx hat. The field stays the same direction. And what do we get? We get the same idea. We have a common factor of LIB, which we factor out. And then we have negative y hat cross x hat. Well, we already know y hat cross x hat is minus z hat. So this is just LIB minus z hat. So this is just LIB z hat. That means on the right side, the forces coming out at us. This is the force on the right side. And so that side of the loop comes out at us and the left side goes in, so you can see it rotates. We can even do more, and hopefully you remember that when you have a rotation like this, a force that causes a rotation around an axis, then the force is best interpreted as a torque. The force creates a torque on the object. So hopefully you remember that from the first semester. So this is sort of like a side view of the loop. But let's just calculate the torque. So what is the torque on the loop? Torque on, whoops, torque, torque on the loop. So we've got the center of rotation here. This is how the axis of rotation. And the force is out at a distance W over 2 on both sides. And it's perpendicular to the axis, it's perpendicular to this direction from the axis of rotation to the application of the force. So the torque, and again, so there's a force here that's going into the board, that's the left force, and a force that's going out of the board, that's the right force. And so the torque, hopefully remember it has a symbol tau. It's just going to be the lever arm, the distance, and the lever arm here is just W over 2. These are like the lever arms. So it's the lever arm W over 2 times the force. Sometimes there's like an angle between the lever arm and the direction of the force, but here the lever arm is perpendicular to the force, right? I'm just drawing the little lever arms there. Okay, so it's W over 2, that's the lever arm distance, times the force, which the one on the left. And they're causing rotation in the same direction, so both of the torques have the same sign. So, all right, so this one, W over 2 times the force, which is just BIL. And then that's from the left side. The right side is also pushing in the same direction. It's got the same expression, W over 2 BIL from the right side. So interestingly enough, they both add together and you get WLBI. But you might recognize that this is just the area of the loop. Because it's the width times the length. So this is also equal to area of the loop times B times I. So that means that the loop experiences a torque, meaning it's going to rotate in the presence of a current and a magnetic field. And the amount of torque you get is proportional to the loop area times the B field times the current that you put in. So, and I guess we can check that the units work out, but it should be kind of clear, hopefully. So let's say our B field is like 1 Tesla. And let's say our current is 1 amp, just as an example. And let's say our loop is a 1 meter squared loop. Then what is the torque? The torque is going to be 1 meter squared times the B field, which is 1 Tesla. And then the current, which is going to be 1 amp. Now, this doesn't look like a torque unit. If you recall, torque has the same unit as energy, has the same unit as a joule. But let's just check to make sure. We can actually figure that out by replacing the torque with something that has forces in it. So you go back here to our expression for the force. We already did the little unit analysis with that. We saw that a Newton is equal to a Coulomb times meter per second times a Tesla. So a Tesla is a Newton second over Coulomb meter. So we can plug that into there. And so we get that the torque is 1 meter squared. And then it's times 1 Newton second per Coulomb meter. And then 1 amp is Coulomb per second. So you have some nice cancellations. Coulomb, second. A meter cancels one of these meters, and you see that the torque for this example is 1 Newton meter, which is the correct unit. That's the same unit as a joule. Okay. So that checks out, and that's the torque that we get on the wire. Now, as soon as the wire, this square loop of wire, as soon as it starts to rotate, um, the torque will decrease because then um, what will happen is, right, the force will no longer be perpendicular to the lever arm when this thing rotates. So we did this from a side view, but let's look at a top-down view of this same situation where you have from the top you would have the wire that's going up is going to be now coming out at us. So this top wire is going to come out if we look at it from the top. So there's a current coming out. It then goes along that top bar, say this way, and then it goes back in here on the other side of the loop. And the center of rotation is like here. Um, and so that's what we get. So that's the top view. And let's set things up again. So if we're looking from the top, the B field, um, we look from the top, the B field is still going to the right. So yeah, so if we look from the top, the B field is still going to the right. So we still have B field this way. Oops, didn't want to do a rainbow one. Okay, so the force that the left and right segments experience is now there's also now going to be a force on the top and bottom parts of the wire, but you don't have to worry about those because they're clamped to the center of rotation. Like a force on that top and bottom isn't going to influence the rotation. We only really care about the forces on these two guys, the left and right, because the whole thing is sort of rotating around. Well, let's see. I want to make sure I get the orientation right of the rotation. So the force is going into the board. So if we're looking from the top view, I guess it's rotating this way, like that. Okay, so let's just check to make sure we understand which way the forces are. So if the current is going out at us into the board on this side, let's set up our coordinate system again. You can use the same one all the time if you want. So on this side, the I is parallel to z hat, and B is still along positive x. So the force the force on this guy over here, the force is parallel to z hat cross x hat, which this is z hat cross x hat. If we go look up in our table, that's y hat. Okay. Z hat cross x hat is y hat. That's good. So there is a force this way, right? There's a force this way. So it is in the right sense. So this is that force on the left side of the loop, looking at from the top down view. And this is after it has rotated for a little bit. For this right one, right, we have the force on this one should be parallel to, now the current is going into the board, so it's minus z hat across x hat. Oh, sorry. Oh, this should have been x, right? X is always the horizontal one. This is y. Oh, so sorry, maybe I messed this up. So let's see. The force, the B is along X hat. That's good. And then, yeah, this is still good. So it's the wrong Y hat. Oh, I drew it wrong. Sorry. Yeah, the force is along Y hat, which is not the horizontal direction, but it's the vertical one. That's right. So it's pushing this thing up. It's the same as it's the same direction as we had before. So if you had a side view of it, it would be into the board. So if you look at into the board direction from the top, it looks like it's going up from the top. So that's the right thing. All right, and this should be this direction should be minus y hat. So it's going down. Right. So the thing is rotating sort of the right way. And this is the force on the right. Okay, so you have the force on the left and the force on the right. And you see what happens is that these guys are going to constantly be pulling down, and the loop will rotate until it's just standing vertically, at which point the torque will disappear because um, once the loop is vertical, so once the loop is like this, where the current is just coming out and then going into the board, then the two forces are just equal and opposite and they cancel. So you have this is the what used to be the left side is now pointing up, and this one is pointing down. And there's no more torque. So that means that it depends on the angle, basically. The um, the amount of torque depends on the angle between the application of the force and the lever arm. The lever arm here is the distance is the direction from the center of rotation to where the torque is applied. So it's this angle right here. And well, you need the component of the force that's perpendicular to the lever arm. And so if this is sort of the right triangle that's relevant for that is this one. It sort of looks like it's a right triangle here. The force on the left and right forms the hypotenuse like that. So this is the force. And then the part we need is the perpendicular. Okay, and I should draw where the theta is. Theta is here. Um, and the part that we need that provides the torque is this perpendicular part right here. So this is F perp, the perpendicular component of the force, and F perp is just the force times the sine of theta because it's the opposite side. So this is the theta. Let me draw it a little cleaner. So this is theta. Um, this is theta. So this is the component of the force that actually provides the torque. So the torque in general for torque on the loop uh, as it rotates, right? The torque is the same as we had before. It's the area of the loop times B times I, but it's only the sine of theta component of the force. So when theta is 0, um, that's the maximum torque. Oh, sorry, that's the loop then is vertical and there's no torque. Sorry. It's when theta is 90 degrees, that's the maximum torque. And that occurs in this situation, um, in this side view. So that's because theta here is 90 degrees for the side view. And it's because the force is perpendicular to the lever arm. See, the lever arm is just the distance, it's the direction from the center of rotation to these side wires, and that's perpendicular to the forces because the forces are in and out of the board here. So, um, and that you can see that better on the top view. So here the angle is this theta, which actually is the same as this theta. So that's the top view of when the loop has already rotated a little bit. You can see that when the loops is at theta is equal to 90, the top view looks like, oh, and by the way, this other one, this other view is the theta is equal to zero case, 0 degrees. Um, so you can see the theta would be like this one. So theta is zero. 90 degrees is, I'll just show you that real quick. Hopefully, hopefully it'll make sense. So you're going through. So this also worked out in the book a little bit, but I wanted to go through it. So here, when it's like that, the this is theta is 90 degrees because the forces are obviously perpendicular to the lever arm, right? This is the left force and this is the right force, and they make perpendicular angles to the lever arm. That's again the direction going from the center of rotation out to where the application of the force is. So if that's perpendicular to the force, then you get the maximum torque. So that's the maximum torque, and this is the general formula for general torque for when the loop is at an arbitrary angle, theta. Okay, so that's how a motor works. Basically, it feels a lot of torque at like 90 degrees, and then it spins and the torque gets less and less, and it hits zero briefly. But it gets enough inertia to keep spinning, and it'll just spin up and convert basically electrical energy from the current to mechanical energy, the kinetic energy of rotation. Okay, and hopefully you saw that when you plug in numbers, the units do work out as you would expect. You get a true torque, which has units of Newton times meter. Okay, so the last example is the Hall effect. This is a more detailed look at what happens inside a wire. Um, it's what happens inside a wire or like a conductor in a B field. So imagine you have a conductor that I'm going to draw it as like a little block like that. And I'm going to put the current in there. Let's say the current is going this way. And let's say it's experiencing a B field that's coming out at us, out of the board. So there's a B field everywhere that's out of the board. Now we know that that means that there are electrons moving in the opposite direction. And what happens is that the electrons will experience a force, right? It's the usual thing that the force on the electron is, let's consider a single electron now, or a single electron. We know it's minus E, and it's going, and it's V cross B, right? And V in this case, we can again set up a coordinate system. If we don't want to do right-hand rule, again, we have X, Y, and Z. So V is just minus the magnitude, and I guess it's going in negative, so it's negative X hat. It's negative X hat. And then B for us is going out of the board, so it's just B times Z hat. So we can just plug these in there into the force, and we get that the force on the electron is equal to minus E, and then V is minus V x hat, and then it's cross product with B z hat. So these cancel the minus signs, and you have E, V, B, and then it's x hat cross z hat. So then again, we have to go look in our table, see what x cross z is. X cross z is minus y. So there's a force in the minus y direction. That means these electrons in the conductor are going to get pushed down. There's going to be a force on them that's pushing them down. Um, so these guys get pushed down. And that means they will accumulate. There'll actually be net negative charge accumulating on the bottom side of the conductor. And since those are electrons are canceling, the positive charge in the material, there must be an unbalanced amount of charge on top. So there's going to be positive charge on top because if the electrons are being sort of pushed down onto the bottom and collecting there, then, since the net charge on the conductor is zero, those electrons must be leaving behind some positive charge on top of the conductor. But once you're in this situation, you see it's a little more complicated because these electrons, they're going to be attracted to the top surface. There's going to be two fields on this, two forces on this electron. One is the magnetic force that we just figured out, this F. But as the charges accumulate on the bottom and top, and there's this charge separation, there's going to be an electric force. The electrons that are moving through here are going to want to be attracted to this positive charge that opened up for them. So there's going to be an electric force. There's a compensating electric force. And what is that force? It's force from the electric field. Well, it's just the charge that we have times the electric field that's there, that's created by the charges. So that's minus, for the electron, it's minus E times the electric field. Well, what kind of electric field do we have? The electric field, remember, it goes from positive to negative. The electric field is this way, right? This is the electric field. So the electron is going to be pushed up. It's going to be pushed up. And because the electric field is going to be pointing down from positive to negative. So the force on the electron is minus E, and then we could say that this is some magnitude E of the field, and it's in the negative y hat direction. So this is E, the electric field, times y hat. Little e for the electron charge, big E for the electric field, and it's y hat. And eventually, charge will accumulate until the electrons no longer feel a force, right? Charge will accumulate until the electric and magnetic forces cancel, because once they cancel, the electrons are just going to be free to move through the conductor, and they're not going to collect anymore on the bottom there because they'll no longer feel a net force. So eventually, net force on the electrons is zero. Net force on electrons is zero. So that means that the forces must sum to zero, right? The force due to the electric field plus the force due to the magnetic field has to equal zero. Eventually, after the electrons have collected and established this electric field to cancel, to compensate for the magnetic field. And so when that happens, we can plug in here and we have E y hat minus E V B y hat is equal to zero. And you can see that will happen when the electric field minus when this, so this is the condition for it, right? Is when this guy cancels that guy exactly, right? That's when there's no more force on the electron. And that happens when this is true, when the charge times the electric field minus the charge times the speed of the electron times b is equal to zero. So we rearrange, right? The e's cancel, and we see that the electric field grows until it gets up to this magnitude, right? It means that electrons will collect and collect and collect and create more and more electric field until the electric field is equal to the speed of the electrons, which is really the drift velocity, times the B field that we have there. And as soon as that happens, there's no more force on the electrons and they just sail on through the conductor like they normally would. So this is called the Hall effect, this collecting of charge that happens. And it corresponds to a potential difference. So we know that if there's a bunch of plus charges, right, and a bunch of minus charges, and they're making a field E in here, then we know that corresponds to a potential difference. We know that the magnitude of the potential difference is um, related to the magnitude of the electric field as follows. It's the change is the potential difference, delta V. So the potential difference over the like the distance between the positive and negative charged plates. So I guess if we go back here and let's define the sort of distance between the top and bottom of this conductor. You're running out of colors in here, but maybe this one. Okay, so we define this distance as d. Then the electric field magnitude is just the potential that develops, delta V, divided by d. That's the relationship between potential and um, between the potential and the electric field. Okay, so let me wrap up then. And this is called, when you have this potential difference, it's usually given as another symbol for the letter. It's usually called this like Hall effect EMF. So it's given this squiggly E. And the D is like the separation, is the width of the conductor, like the height of it. And this is equal to the drift velocity times B. So we can solve for the EMF. And the EMF is just equal to um, the magnitude of the B field times the distance, the sort of thickness, the width of the conductor, and times the speed of the charges that are going through there. So this is the charge speed, the drift velocity for electrons. This is the width of the conductor. And this is the magnetic field. And that's magnetic field magnitude. And this formula is basically used to figure out. So you would typically measure this. So you can measure the EMF. And if you know the magnetic field and you know the width of the conductor, you can figure out like the charge speed, which is usually what this is sort of used for. In particular, if the charges are not electrons, but something else like ions or something, then it can be used to figure out the velocity of like the fluid or whatever is carrying the charge. So this is used actually for measuring blood flow. So let me just say that this is the last example for blood flow. So the way this would work is you would send a blood vessel in. Oh, sorry. You'd have a blood vessel that's and you're trying to measure the speed of the blood, V. And what you do is you put the blood vessel in a magnetic field. You apply a B field to it, say like, out of the board or something. We can make it the same setup as sort of this. Yeah, so say that you apply a B field that's out of the board. This is our B field. And what you do is you take a little probe, like a potential, like a multimeter type probe, like to measure voltage differences. And you measure the voltage difference between the top and bottom of the blood vessel. You measure like the EMF. So you have a little voltmeter. And if you know the magnetic field and you know like the diameter of the blood vessel, so let's, like this distance, this is D. So I use D because usually you don't usually have like a square wire. It's usually a circle, but it's easier to draw the square to show the charge accumulation. But anyway, if it's a cylindrical wire or a blood vessel, then, this is like the diameter. Anyway, so this is the relationship. So you measure in volts this EMF, you measure it. And we know that it's related to the magnetic field, the diameter of the blood vessel, and the speed. So you can actually figure out, like given a certain Hall EMF, say you measure this at, I think a normal value is like 100 microvolts. So you measure that with your probe that measures, you can measure the potential difference across the blood vessel. And let's say you applied a field, say, of 0.1 Tesla. By the way, a Tesla is like a big field. So you normally you would have a much smaller field um, in like a lab setting, smaller than a Tesla. So like a tenth of a Tesla is reasonable. And then you might know that the diameter of a blood vessel is, say, like 4 millimeters. So if you measure the EMF, it actually tells you what the blood velocity is. So we can extrapolate what the blood flow, what the speed should be. Because the blood is carrying ions and things like that. You can see that the cool thing about this is that this doesn't actually depend on the magnitude of the charge. It's really kind of strange. The magnitude of the charge just has to do with like how much charge will accumulate there. The actual expression that you get in the end is independent of the charge value. It's very surprising, I think. It's not obvious that it would work out that way. So it all only depends on the speed of the charges. So your blood will carry ions and stuff in it, and no matter what those are, as long as they're there, they will produce a Hall EMF that you can measure. And the Hall EMF, this funny letter thing, that'll tell you about the speed of those charges going through. So it's really very impressive that this works that way. I don't know. It's kind of counterintuitive. You would think that it would depend on the nature of the ions in the blood vessel, but it doesn't. So, okay, so let's solve for V. V is equal to this EMF that we would measure with like a probe of some kind, divided by the magnetic field times the diameter of the blood vessel. So if we have 100 times 10 to the minus 6 volts here measured, microvolts, so it's 10 to the minus 6. We have 0.1 Tesla for the B field, and the diameter is, say, 4 millimeters, so that's 0.004 meters. We plug everything in. Again, use a calculator. I guess I could have simplified this a little bit, but let's just, again, do the calculator thing real quick, just make sure I get all the powers of 10 right. Okay, I get that it's 0.25. And it should be meters per second because that's the SI unit for speed. But we can check that these funky units actually reduce to what we want. This is maybe a little overkill, but I don't know. I think we probably should at least once. I have unlimited time here, so um, okay. So we know a Tesla is. See, back here we had a Tesla is a Newton second over Coulomb meters. Newton second over Coulomb meters. Okay, that kind of helps because, and then we need a volt. We need a volt. A volt. We need to get rid of the Coulomb. So I have to remember how volts are related to two things. So we know that if we multiply volts by coulombs, we get energy. So actually, this is a Newton meter, which is a joule per coulomb. So actually, this I think will give us the right thing. So all right, if we replace volts by Newton meter per coulomb, and then we're going to divide by Tesla times a meter, which is just a Newton second per coulomb. Okay, so then this becomes 0.25. I have Newton meter per coulomb. And then this is in the denominator. So if I flip it to the numerator, the coulomb goes on top and the Newton second goes on bottom. And magically, lo and behold, the coulombs and newtons cancel and you get 0.25 meters per second. And that's quite a reasonable value for blood flow. That's 25 centimeters per second. Um, and again, I want to emphasize the amazing nature of this. You take a blood vessel, you stick it inside a magnetic field, which you know, okay? Of course, the blood is carrying all sorts of cells and, a bunch of stuff. But among those things are ions, are charges. So it has some kind of current. And because it has that current, it'll generate a Hall EMF. It'll create the separation of charge. And you can actually measure that in volts. And from that, you can extrapolate how fast the blood is going inside. So pretty amazing. Yeah. All right. So those are the three examples. Again, they were the Hall effect, which is section, I think, 22.6 in the book. They were the motors, which is a little bit later. I guess it's 22.8 in the book. And the other thing was the two parallel wires. And that's from the lab that we missed, but in the book, it's section 22.10. All right, so I know this was long, but hopefully it'll be useful. And thanks for listening.